All right, welcome back. Last week we started discussing a new equation of motion called the Dirac equation. And the Dirac equation, the motivation for studying it is it will turn out to be the right way to build quantum fields for fermions with intrinsic spin. That wasn't quite the original motivation for the Dirac equation, but that's the one we'll use in this course. And to summarize the steps that we went through last lecture, we introduced new representations of the Lorentz group by producing these auxiliary matrices here, these gamma matrices, that obey these particular anti-commutation relations here. And when we found a set of such gamma matrices satisfying these anti-commutation relations, it turned out to be possible to build new representations of the Lorentz group. These representations will have intrinsic angular momentum, as we'll see later. And from those, we could build a new equation of motion that was Lorentz invariant. And we proved that that was Lorentz invariant in the previous lecture. So today's tasks are to, well, one is to write down a Lagrange density from which this comes, so that we can then eventually find a Hamiltonian density that we can then guess a quantization from. So that's one objective today. Another objective today is to study this equation in the limit of zero mass. So now it decouples into two equations, which are also Lorentz invariant. And the final objective for today is to actually solve it as a wave equation. And these solutions will be the free particle basis that we'll later use to build our quantum version of the Dirac field. So those are the objectives today. And each of these points is not particularly complicated. We just have to get through some derivations in order to actually build these things. The zero mass limit is actually rather interesting when you get into studying supersymmetry, but that's nothing we're ever going to do in the courses of the next semester. Good. So let's find now a Lagrange density for the Dirac field. Right, so we've got this thing here, psi. That psi is a spinor, a Dirac spinor. Remember what a Dirac spinor is? It's something that transforms according to lambda a half. So something is a Dirac spinor when, if you look at it in a different reference frame, it looks like this, and that's a definition. And we wonder, can we build a Lagrange density for the Dirac field? So to do this, we're going to need some scalar quantities. Some Lorentz scalars. And using these Lorentz scalars, we'll then try and build a Lagrange density such that when you apply the Euler-Lagrange equations to it, you get back the Dirac equation. So that's the objective 1 for today. Now, the first guess which is wrong for a scalar quantity from the Dirac field would be just take the adjoint of this Dirac spinor field. Right, that's your first guess. Should be your first guess if you're used to things that transform according to unitary transformations. But, and we knew this all the way back in lecture 1, our representation of the Lorentz group cannot be unitary if it's finite dimensional. So this lambda a half that appears in the transformation law for the Dirac spinor, that lambda half is a representation of the Lorentz group. It can't be unitary. So under Lorentz transformations, this transforms to that. And it is not generally the case that lambda a half dagger times lambda a half is the identity. So this is a failure, right? This thing here is not a Lorentz scalar because in a different reference frame, well, it doesn't have the same form. So this is sort of slightly bad news for guessing Lagrange densities. But it turns out there is a quantity that you can build that is a Lorentz scalar. This quantity here is a Lorentz scalar. This is not obvious. It shouldn't, it shouldn't leap out at you that that's correct. So we're going to define a thing called psi bar, and to prove that this is a scalar, we're going to need a little lemma. A nice little piece of matrix analysis lemma. Namely, that lambda half dagger gamma naught is equal to gamma naught lambda half minus 1. So the gamma naught takes care of the bit that doesn't cancel and converts this into an inverse. So this is a lemma, and it's, as I said, a nice bit of matrix analysis, and the proof is left as an exercise for you. And given this lemma here, then we can easily see that in a different reference frame, psi bar psi has the same form. We make a Lorentz transformation. We get a lambda half dagger here, a lambda half here. Lambda half goes past the gamma naught to become lambda half minus 1, which is then equal to the identity when multiplied by lambda half. And then we end up with psi bar psi again. I'll just say just to amplify this point here, lambda half is not necessarily a unitary matrix. That's why that's not a scalar. So following on from this observation here, we can build vector quantities from spinors. So if you define V mu, this 4-component vector V mu, as psi bar gamma mu psi, then you do a Lorentz transformation, then V mu transforms to lambda mu nu V mu. V nu. So it transforms as a Lorentz vector. I'm saying Lorentz vector here because we've got vectors in the sense of vector spaces, which shouldn't be confused with vectors in the sense of Lorentz vector, transforming like a Lorentz vector. It's a somewhat annoying problem that one has with spinors. And is that what I wanted to say? Yep. Okay, and now we actually have all the ingredients to write down a Lagrange density for the Dirac equation. So we know how to build scalars, we know how to build vectors, and that's all we need actually to give us this Lagrange density. So this is psi bar, not a minus but an I, gamma mu d mu minus m psi. That's a perfectly respectable scalar quantity. And it's also an exercise to prove that that's a scalar. And it's also an exercise, and a pretty good one, to do the Euler-Lagrange equations as well. And to recover the Dirac equation. I hope you're getting pretty good at the Euler-Lagrange equations now. You should already have a sense in which that does give you the Dirac equation if you use psi and psi bar as independent variables. So we found a classical field theory which has the Dirac field as its equation of motion. We'll study the stress energy tensor for this field theory a little later, and we'll discover its angular momentum properties. But before that, we should just comment on where we're going. Where we're going, of course, is we're going to try and guess a quantum theory that has as its effective classical limit this free classical theory here. And remember the way that I taught you to guess these quantum theories, you just put hats on the operators. And that works rather well, usually. However, in this particular case here, we should work a little harder to get the Hamiltonian first so that we can guess the Hamiltonian. And then when we put the hats on the operators and impose commutation relations on the resulting operators, we'll see that it makes more sense to use anti-commutation relations than it does to use bosonic canonical commutation relations. So in the next part of the lecture, We're going to analyze a little bit the properties of the Dirac equation in the zero mass limit. And then we'll get to the Hamilton. Am I going to do the Hamilton? I guess I'll do the Hamilton density now, because that connects better, doesn't it? So we're going to work out the Hamiltonian for the Dirac field, and we're going to do that by first working out the conjugate momentum. And you find out that the conjugate momentum to psi is in fact I psi dagger, psi bar. And that leaves us with the following Hamiltonian . Like this. So if you do the standard replacement of the conjugate of the time derivative of the canonical coordinate psi with the conjugate momentum I psi dagger, then this is a well, also an exercise. We end up with the following Hamiltonian here. So this notation here simply means the sum over the spatial indices. I won't do this. Like that. And I hope it's clear that the I psi dagger is the conjugate momentum because in the Lagrange density, the time component, d naught, we have the d naught psi, which is what's giving the momentum in this transformation here, is multiplied by gamma naught, right? Gamma naught d naught psi. But the psi bar has an extra gamma naught in it, and gamma naught squared is the identity. That's why we get this I psi dagger for the conjugate momentum. And that's why this looks a little bit asymmetric here, this description for the Hamilton density for the Dirac field. So that's our classical field theory done in the sense of writing down a description of the dynamics of this classical field. Before we actually solve these dynamics, right, before we actually do some real physics, we're going to first study a very important limit, the limit where the mass of the field is 0. Okay, there's something that's really interesting that happens when we set the mass term to 0. Turns out the equations of motion decouple when the mass is 0. So let's see. So recall that the Dirac equation in this particular solution for the gamma matrices that we've chosen before has this particular structure here. So let me actually just check that that's the case, that I haven't misremembered. No, that's correct. Now if this mass term was 0, then these 4 equations, well, this set of first order partial differential equations here would decouple, right? It's only the mass term which is coupling the components of this spinner here. So psi, recall also, right, that psi of x is a 4-component object. And we'll see that in the zero mass limit, we get 2 separated equations. Now, to make that clear, we're going to write our 4-component Dirac spinner as two-component Dirac spinners, not Dirac spinners, two two-component spinners stacked on top of each other, like this. This is going to be useful later on when we actually solve the Dirac equation to think like this. Kind of think of this as the left mover, the right mover, if you like. So it's convenient to do that. And we're going to see the consequences of this in the case where the mass is 0. Okay, so these two component objects there, they're called Weyl spinners. And it turns out that under a Lorentz transformation, they transform into themselves. Yeah. And these 6 parameters, theta and beta, correspond to the rotation and boost parameters for the Lorentz transformation. All right, so this is just a pure observation so far. Now, if you look at the transformation law here for psi L, it looks almost the same as the transformation law for psi R, right? There's hardly any difference between these two. It turns out the top one contains implicitly the transformation law for the second if you do a certain transformation first. So we can get the transformation of psi r from psi L by taking the complex conjugate and multiplying by sigma 2. This operation here is called the spin flip because on the Bloch sphere it takes a Bloch vector pointing in one direction on the Bloch sphere, and it gives you the inverse Bloch vector pointing directly at the antipode of the original Bloch vector. And that means, if you apply that observation, then you can get an object transforming like psi r by taking an object that transforms like psi l, complex conjugating it and multiplying it by psi 2. All right, so that's pure Lorentz transformations. They're just like rotations in Minkowski space, right? Rotations, but not translations. So according to just rotations in Minkowski space, these actually decouple. It's when you add in translations, you talk about the inhomogeneous case where of the Poincaré group, where you include rotations and translations, that these objects actually transform into each other. So they are coupled, and they're coupled by translations in time. And also in space, I think. I haven't worked that out. And to see how they're coupled, we're going to write out the Dirac equation in terms of these psi L Weil spinors, and we'll see that the Dirac equation couples them unless the mass is 0. So, well, it's a little exercise. It's hardly any. We've already done most of the exercise last week. Right? So that's the Dirac equation there in terms of these Weil spinors psi L and psi R. Psi is missing there. So something to observe straight out is that the value of psi L depends on the value of psi L and psi R in the solution of Dirac equation here. So when the mass is not 0, the two halves of the spinor are coupled. But the thing to notice is that if the mass is exactly 0, then the equation of motion for psi L, it decouples. It doesn't depend on psi R any longer. And we have two independent solutions. And these, in this zero mass limit, we actually obtain a representation for the Poincaré group, not just the Lorentz group. That's two-dimensional. So I kind of said a lie in the previous lecture that you need gamma matrices that are 4 by 4 to build Lorentz invariant equations of motions for particles with intrinsic spin. It's possible with lower dimensional systems, but the mass has to be 0. And this process of defining these psi Ls and psi Rs will help us very much when we're trying to solve Dirac equations. So our next task is that. We're going to take a look at this equation here and actually solve this linear partial differential equation, or the system of linear partial differential equations. And it's precisely this observation here that will be extremely useful in trying to build our solution. So when m equals 0, as I said, these two equations decouple. And we get two independent equations for the different Weyl spinors. So physically, this is rather interesting. It's possible to attach to fundamental particle, some species of fundamental particle, the description in terms of a Weyl spinor, as long as that fundamental particle had zero mass, like exactly zero mass. So we could build field theories in terms of just psi L's or just psi R's. And that'll turn out to work out in the quantum world to some extent as well. So the real building blocks of fermionic field theories are not Dirac spinors, but actually these Weyl spinors. And it's only when you add a mass that you need to deal with Dirac spinors. Now there's some useful notation that we'll use. When we're talking about solutions to the Dirac equation, it's this one here. Vectors of these Pauli matrices. And in terms of this nice notation, our representation that we've been using so far looks like this for the gamma matrices like that. And the final consequence of this nice notation is that these Weyl equations look even prettier in terms of this sigma and sigma bar notation. We see that we can write these two Weyl equations, independent Weyl equations, in terms of sigmas in this highly compactified notation there. All right, so that's everything I want to say about the Weyl equations for the moment. I guess we're not going to encounter them again until next semester when we talk about symmetry breaking. I don't know if we encounter them again. Certainly don't think so in this course. They're super useful when you want to talk about supersymmetry. Super useful, right? Good, let's get now to the main course. The main course for today will be solving the Dirac equation. This is fantastic. We can actually get a complete solution to this equation. It's extremely elegant once we've got this notation in hand. And I guarantee once you've seen it, you'll love it, and you'll want to forget how you got to it. So the first thing to note about the Dirac equation is it's a linear equation. It's a linear PDE. It's a linear system of PDEs. So the way you should think to solve those kind of equations is just do a Fourier transform and you're done. That's the moral of linear systems of PDEs. Fourier transforms exploit the translation covariance of the equations. Answer done, right? So, but the devil is in the details a little bit. We have to deal with 4 separate components for this Dirac field. And that can make things slightly awkward when trying to solve it. But at the end, we'll find a neat trick to express our solution in a super compact form. So Fourier theory should tell you, at least in the absence of sources. So if you have any sources, then we have to use green function methods. But in the absence of sources, the solution may be expressed in terms of plane waves. It's just the Fourier transform. And a plane wave for a Dirac spinor, what could that be? Well, the simplest thing it could be would be e to the IPx, right? That's the plane wave bit. Am I using p or k? P. E to the IPx, minus IPx, let's say. But that's a scalar, right? And we know that a spinor is a 4-component vector in a complex vector space that transforms as a spinor rather than a Lorentz vector. So we need to somehow turn this into a vector, a 4-component complex vector. Well, simplest way we could do that is choose some constant 4-component complex vector, UP. And that would be a plane wave solution to the Dirac equation. And then linear combinations of these should give the general solution to the Dirac equation. That's your standard approach to solving linear PDE. Now, there's some constraints, right, where firstly we want to be on shell. So we want this to be an actual physical momenta of a particle. And suppose further that P naught is greater than 0. We want a positive energy solution. It turns out we'll have to also consider negative energy solutions. Let's call it, I've called that star, so let's call this star star. We're going to substitute star star into the Dirac equation and see what comes out. So the whole beauty, of course, of a plane wave solution is that whenever you've got an e to the minus IPx and you differentiate it, it just brings down a component of the momentum vector p, momentum 4 vector p. So the answer, do I have it on the board? The Dirac equation? No. And this minus cancels out. So it's this, right? Let me just check that. Yep. It's all good. So this is not a differential equation at all. This is just a matrix equation. So gamma mu is a 4x4 matrix. We've got a linear combination of 4 4x4 matrices, so this is a 4x4 matrix. There's always an implied identity matrix in here. So that's also a 4x4 matrix. So this is just of the form of A times X equals 0, where A is a matrix and X is a vector. We have to find a vector X, which in this case is the U, P, such that when I multiply that vector X by this matrix A, you get 0. So you need to find a 0 eigenvector of this 4x4 matrix here. Now we're actually going to find the general form for that, But there's this trick, right, the physicist's trick of making one's life easier by spending symmetry. We're not going to write out the full solution like that. Instead, we're going to go to the rest frame, because everything's covariant, solve the equation there, and then boost back up to the general reference frame. And then in the end, we'll actually have an expression for this solution here. Be very elegant. So as long as we can find a U of P which is annihilated by this 4x4 matrix, then we're golden. Now, of course, there might be one zero eigenvector of this matrix here, but there might be 2 or 3 or 4. Turns out that the linear space of x's that satisfy this equation here is not one-dimensional, but in fact two-dimensional. We'll have 2 linearly independent vectors that solve this matrix equation here. Which is great, right? We have 2 solutions, 2 linearly independent solutions to the Dirac equation. But when you look at it in this form, you see that there must be further linear independent solutions, because psi is a 4-component vector, and we cannot express an arbitrary 4-component vector as a linear combination of 2 vectors. We need 2 more. So we're going to find those additional 2 solutions a bit later. But now, let's first get these so-called positive energy solutions before we look at the other ones. So, as I say, let's go to the rest frame. You don't have to do this. If you could just work straight up in this reference frame here. I don't know, maybe it's a good exercise. I've never actually done that, but I suppose you'd be able to find a solution. So in the rest frame, we know that the momentum 4 vector, well, it has a specific form, doesn't it? It's P naught, and by virtue of the fact that we're in the reference frame, the rest frame, sorry, it must look like that. The momentum 4 vector. So the rest frame of this momentum 4 vector P looks like M comma naught. Has to be. But in terms of that momentum 4 vector P, this equation here, that gets really simple now, right? Because 3 of the terms here is 0. So that equation there, which we'll call triple star, becomes just M times gamma naught. Gamma naught has this form, minus M times by the identity, which has this form. Oops, sorry, we're calling it U, aren't we? Well, that equation couldn't be simpler. Well, it could be simpler, right? This could be the identity, then it would be super simple. This is about as simple as it can be. That's not trivial. So there's always 2 solutions to this equation, not 1. And those are the solutions of the form UL of P equals UR of P. So these 2-dimensional complex Weyl spinors are equal to each other. You can see that is annihilated by this equation. And they're of the form root m times by xi, where xi is some fixed vector. And why on earth this root m? Well, it's there for convenience. You'll see later on that if we didn't put the root m in there, then the answer would look uglier, and then we'd want to put the root m in there. And we're free to choose a normalization for this vector xi. Let's make it just norm 1, because any scalar multiple of it will also be a solution. Now, how many such vectors xi are there? It's a two-dimensional complex vector space of these guys. Therefore, there's two linear independent solutions in the rest frame. All right, I'm going to change some notation. When we work in the rest frame, I'll indicate that by putting a naught on the momentum vector. There should be a naught up there as well. Okay. First thing is 1 and 2. So we get a full two-dimensional linear space of solutions in the rest frame given by e to the minus ipx us p naught minus ipx like this, where psi1 is your favorite two-component complex vector and psi2 is your next most favorite two-component complex vector. Of course, any linear combinations of these two things would do as well. We just break the symmetry by choosing this particular basis like that. Okay, so that's all in the rest frame, right? We go to the rest frame for a given momenta, solve Dirac equation there. But that's not the solution to the Dirac equation. We have to express the solution in the general reference frame. So to get a solution in a general reference frame, we perform a Lorentz transformation. We boost our current solution and look at it in the other reference frame. And we know how to carry out Lorentz transformations on spinors. So we just have to find the matrix and multiply. So I'll do an example, and then we will just write out the general solution. So let's look at a boost along the 3 direction. So the Lorentz transformation for a boost along the 3 direction has a specific form. We can write it out. So this is something you meant to just know from special relativity, that a boost along the 3 direction is represented in the fundamental representation by this 4x4 matrix here, and this eta is called the rapidity. And now we want to find the representation of that Lorentz transformation, this boost, in terms of the spinor representation lambda half. So we need to work out how to express this boost as an exponential of minus I omega dot j over 2. And we've got to work out these parameters omega for this boost transformation, and then choose a different representation, and then work out lambda half, corresponding to this transformation here. And in particular, there's only one non-zero value of omega, it's 0.3. I'll just write it out on a separate board. So remember, all Lorentz transformations can be written in exponential form in terms of these generators here, which obey the Lie algebra of the Lorentz group. And we have these 6 coefficients here, these omega mu nus. So for us, there's only one that's non-zero for this boost along the 3 direction, that's omega 0.3. And that value of omega 0.3 is given by, did I work it out? Yeah, it's the rapidity, right? Okay. The whole point in writing the Lorentz transformation in terms of the rapidity is that it's easy to read off this value of the boost parameter. All right. To do exactly the transformation corresponding to this Lorentz transformation on a spinner, we need to apply the matrix lambda half e to the minus I over 2 omega 0, 3, which equals the rapidity, times by the spinner representation S03. And that S03, question?
Shouldn't there be 0, 3 as indices in the top line of the J?
The question is, shouldn't there be a 0, 3 index up here? Yes, there should. Thank you. 0, 3. Absolutely. Now remember, we have a formula for S03. It's the commutator of the gamma matrix, gamma 0 and gamma 3. And there's like a factor of a quarter or something, isn't there? I haven't written it out. Ion 4, yeah. This is some 4 by 4 matrix, and if you work out that 4 by 4 matrix, you find the following 4 by 4 matrix. Namely, sigma 3, 0, 0, minus sigma 3, and there's some i's missing and some 4's missing. I think it's that, actually. Oh, no, there's a 2, isn't there? A half? Right. I think the minus there is correct, right? Yeah. Minus sign. All right, so that's SO3. And lambda half then equals, well, whatever, e to the minus I over 2 this matrix is. And this is actually pretty easy to calculate because this is a direct sum of two 2 by 2 matrices, and exponentials of 2 by 2 matrices is doable, right? So there's a factor of a half discrepancy with my notes, which is what's stopping me here. I think there's a factor of 2 error here, which is not easy to determine at this point. Well, let's let eta equal 0. That's no help. And yeah, then this is going to be an exercise, I'm afraid. I think there's a factor of 2 difference between these two, but I don't want to spend 20 minutes working out this exponential here to work out if there's a factor of 2 or not. But I think it's more than likely that I've made a factor of 2 error. Assuming that's the case, then this transformation here should look like this. Now this is a calculation that's so simple we can just do the answer, right? Because sigma 3 is diagonal. It's 1, 0, 0, minus 1. So the exponential of minus a half eta sigma 3 is also easy to work out because it's already diagonal. It's just e to the minus a half eta, 0, 0, e to the a half eta. So you could either ignore that hint or believe what I'm about to write. Well, actually that wasn't so hard. So in the the boosted frame, our solution looks like the following. P naught here. And here comes a cool observation about 2 by 2 matrices. It just so happens that you can write this slightly differently as that one's for you. That's an exercise. And I guess the way you could convince yourself that it's true is there's this fantastic matrix identity for Pauli matrices. So this is a fact about 2 by 2 matrices that will be very useful to you in doing this calculation. Now I didn't have to do this, right? I could have just left it like this. That's also fine. That's a solution in the boosted reference frame. And writing it in this cryptic way here, there was a reason for it, and that's because if I any other boost, the solution would look exactly like this. So it happens to be true for a boost along the 3 direction. The exercise is to prove that it's true along a boost in any direction. It's actually not so difficult because you just rotate, right? So you just have to work out how to rotate. And it's going to be this. This will actually be the general solution. Yep.
Are you missing something, or do you have to parameterize the u with an s? Because these theta of s.
Oh yes. Yeah. Your question is, where's the s up here? The s is up there. Yes.
What is about this exponential function in the solution in the rest frame?
You asking about this?
No, the other one. If you look at the board after this one, there's
Up there?
yeah.
Ah yes.
For the u.
Oh, there should be a p naught up in the exponential function.
On the left side of the equation, there's an exponential.
Oh gosh, yeah. What's that doing there? No, that's correct. Yeah, the general solution looks like this.
Yeah.
Don't we have to have that here? Yes, we do. Ah, gosh. Thank you. Yeah. Yes, you're absolutely right. Yeah. So the general solutions look like this. Psi. Good. Well, I have a couple more minutes to get the other two. So what we've got so far are 2 linearly independent solutions to the Dirac equation in a general reference frame. But we don't have the other 2. We know there must be 4 for a given momenta. And the other 2 come from negative energy solutions, negative frequency solutions. So we get two more linearly independent solutions when we look at the negative frequency ansatz there. So similarly to the U case, you can go through to the rest frame, write out the Dirac equation, but notice you've got this plus here, so you get plus signs, we had minus signs before, and minus signs, we had plus signs before. And we get these two solutions here with the actual exponential function there. And it's kind of stupid, I guess. Similarly to positive frequency case. And the whole point of this root m that we had up here, remember we had this root m up there, was to facilitate this observation that you could express the solutions in terms of this root p dot sigma. Okay, and I guess the last thing I want to say today is just about normalization. What do these guys' solutions look like? How do we normalize them? So psi bar psi is Lorentz invariant. So this is how we're going to take our inner products. So when psi equals one of our two fundamental positive frequency solutions, psi bar psi is pretty easy because you've got an adjoint which gets rid of this phase factor. And then you just end up with US bar US P. And that is a very nice exercise. Like that. And similarly, when we get the VS solutions, exactly the same thing happens. And I'll express the full linear independent solutions. Yeah, here we go. Okay, it's not hard to see that U bar RP, USP is equal to this Kronecker delta function. Similarly for these V's. Except there's a minus there. And finally, there are some relations between these two different solutions, the U's and the P's. So URP VSP is equal to VRP USP, which is equal to 0. So we have 4 linearly independent solutions to the Dirac equation in a given reference frame. And yeah, it seems like a convenient moment to stop. In the next lecture, we're going to take these classical solutions to this classical field and quantize them. That means we're going to cook up some quantum operators whose commutation relations obey the canonical commutation relations, and then we'll see that that's probably a stupid thing to do and try the canonical anti-commutation relations. And then we'll cook up a nice representation of the Poincare group in terms of a thing called the Dirac quantum field. Okay, thank you very much.